Hello viewers, Wagadaruna taking you through this tutorial for A-level applied mathematics. And this video we are going to go through the topic of center of gravity. So this video is suitable for students in both Senior 5 and Senior 6 offering principal mathematics as part of their combination. So before we proceed, this is the course outline for Math Paper 2. And what is ticked is what is already available on this platform. So today we are going to cover the video for center of gravity. And there are also some books which are vital at this level, in A-level. For principal mathematics, there are 4 books. There is Math 1, Math 2, Termly Participles, and Topical Question Bank. Subsidiary mathematics is only 1 book. Then for physics, there are also 4 books: Physics 1, Physics 2, Topical Chubi, and its solutions. For any of these books, contact the author on this contact. So we shall start our topic of center of gravity. There are 2 terms which are needed. One is called uniform body and the other is called lamina. So a uniform body, actually for center of gravity at our level, is only for uniform bodies. Non-uniform bodies, we don't cater for that. So a uniform body is made from a uniform material, i.e., any given quantity of the material measured by length or area or volume will have the same mass at any equal quantity of the same material. So this is what they mean. For example, I have this dimension. I cut off 1 centimeter, 1 meter, 1 meter here, and I measure its mass. I also come and cut on another portion, 1 meter, 1 meter, 1 meter. Because they are of equal dimensions, they must have the same mass and the same weight. That's what they mean by uniform body. If they are different, it means that the weight of this body is not evenly distributed, meaning that it will be non-uniform. But for our case, we shall only concentrate on uniform bodies. Okay, so it follows that a uniform body will have mass equally distributed about any line of symmetry. So that center of gravity of a uniform body lies on each of the lines of symmetry that the body possesses. So when you look at a body, if it has a line of symmetry, then the center of gravity must lie along that line of symmetry. If it has more than 1 line of symmetry, then the center of gravity must lie at the point of intersection of the lines of symmetry. That is a uniform body. Then a lamina is a flat body whose thickness is negligible. Remember, volume of a cuboid, we get it because it has a thickness which is not negligible. But what if the thickness is negligible? What would happen? It becomes a lamina. So here we can only consider length and width alone for a lamina. Uniform lamina has the same weight per unit area. So this is what we shall be using more frequently when we reach at the step of getting center of gravity of various laminas. So here go step by step. This video is subdivided in something like 4 parts. The first is center of gravity of particles, then centroid of a lamina, then center of gravity of a lamina, centroid of solids of evolution, and center of gravity of solids. I think those are 5, so we shall look at all of them in this video. Now let's start with center of gravity of particles. So consider particles of weights with magnitude W1, W2, W3, and so on up to Wn, meaning they are n particles. Situated at positions x1, y1 for W1, x2, y2 for W2, x3, y3 for W3, and so on up to xn, yn for Wn, respectively referred to coordinate axes or x and or y. The center of gravity G. So G is a letter which is commonly used to denote center of gravity. And x bar, y bar is the coordinate of the center of gravity of the overall particles. Of these particles in the xy plane is obtained by taking moments about x and y axes. So what is the difference between the two axes? If, remember, you are like this is the x-axis and this is the y-axis. So if I want to get y bar, I'll take moments about the x-axis side. The distance I measure are on the y coordinates or y distances. Then if I want to get x bar, I'll take moments about the y-axis. So the distance I measure are along the x coordinates. So that's the difference. When you take moments about x-axis, you get y bar. When you take moments about y-axis, you get x bar. As simple as that. So at equilibrium, we'll say that sum of moments of all the particles is equal to moment of the sum of all the particles, which usually call the resultant. That's why here we say, that's what this formula is. You see here, it is weight times the position vector. And then you sum all those ones. So weight times position vector gives you the moment, but you have to sum up all the particles. That's what they mean by sum of moments. Then moment of sum means you sum up all these weights, which is here, and multiply by the position vector of the overall center of gravity. So let's see how to use that formula we have quoted. Question 1 came from UNEB 2013, paper 2, question 12A, and says, particles of masses, these ones, act at points with position vectors. So we remove this, with position vectors, these ones, respectively. Find the position vector of their center of gravity. So shall recall that sum of moments is equal to moment of sum. Sum of moments, you add up all the particles, this with this, this with this, this with this, and this with this. Then moment of sum, you add up all these masses. Now I think you realize there is the G here. Why? Because they said center of gravity. There are two words, the center of gravity and center of mass. For a uniform body, the center of gravity, center of mass, centroid of a particle, they all at the same position. So what differs is that when they ask for center of gravity, we use weight. That is why from kilogram, we converted it to weight to become 5G. Even this one to weight, to G, to weight, 3G, to weight, to G. If they had asked for center of mass, we would not include this G, and the position will still be the same. Then we can add everything. So add, first of all, this G cancels throughout. So remain with this times this, plus 2 times this, plus 3 times like this, plus 2 times this. It gives you 11. Then the y coordinate 5 times this, plus 2 times this, plus 3 times this, plus 2 times that, to give you 12. Then add all these ones, 5 plus 2 plus 3 plus 2, to give you 12. Then take this 12 this side to come up with this. Using a calculator, you come up with this as the position vector. And that's what they wanted. Question 2 came from UNEB 2011, paper 2, question 8, and says, particles of weights this act at points these ones, respectively. Find the center of gravity of the particles. So we still got the formula. Sum of moments is equal to moment of sum. Then you come and substitute. And then use a calculator. Take the 24 on one side to get the x bar and y bar. And that's what they wanted. Then question 3, source came from UNEB 1997 part 2, question 4, and says, particles of mass, these ones, placed at these points, respectively, are in the xy plane. Find the coordinates of their center of mass. Now here they have used center of mass, meaning we don't need to get the weight. We only use the masses as given. However, if you also use the weight, the answer will be the same, but it will be a wrong approach. So x bar is that and y bar is that. Then you can get the coordinate. Question 4 came from UNEB 1996 part 2, question 9a, and says, find the position of the center of gravity of 3 particles of masses, those ones, which lie on the y-axis at point these ones, respectively. So sum of moments is equal to moment of sum. Then you substitute. Now here they said center of gravity, that's why we're putting in the G. Then add up everything, get the x bar and also y bar. And that's what they wanted. Question 5 came from UNEB 2007, paper 2, question 2. So I've done a number of examples for you to grasp this first part, then we shall go to the next part of the center of gravity. So question 5 says, find the position vector of the center of gravity of a uniform lamina in the form of a triangle whose vertices are these ones. So now this is a little unique from what we have been doing. But what we need to know that if those coordinates are vertices of a triangle and a triangle is the lamina, then the center of gravity is got by getting the average of each coordinate. So the x coordinates, get average of all the x coordinates, and also the average of all the y coordinates. It gives you the coordinate of the center of gravity, as simple as that. Position vector, you write in vector form. So that has been center of gravity of a particle, of particles. Now shall go to center of gravity and centroid. Are they the same or they are different? Let's see. Centroid is the geometrical center of the rigid body. For example, for a rectangle, it is the point of intersection of the diagonals. For a triangle, point of intersection of the medians. Okay. For a body whose weight is uniformly distributed, the centroid will also be the center of gravity. But for an object whose density, in brackets mass per unit volume, is not constant, they could be located at different places. So like I told you here, we shall be interested in uniform bodies, meaning that centroid and center of gravity, they will mean the same. You work them out the same way. Based on the scope of the syllabus, we shall only consider uniform bodies and shall regard G as constant. Consequently, center of gravity, center of mass, and centroid will all be located at the same point. Why? Because the body is uniform. So let's look at centroid of a lamina. So in centroid of a lamina, we need to bring in some of the calculus which you covered in math paper 1. So centroid of a lamina is the geometrical center of a lamina. We already saw that. So consider a lamina bounded by the curve, this, the x-axis, and where necessary the lines x equal to a and x equal to b as shown below. So let's make a simple sketch for such a curve. So we have the axis, then we bring the curve y equal to fx. We also have the lines x equal to a and x equal to b. So this is the area enclosed. So the question is, can we get the center of gravity of that enclosed area? How to get it? Because this doesn't have a definite shape whose formula for area is known, then you have to use knowledge of math paper 1, which is calculus. So we're going to divide the area in two small strips. So the height will be y and the thickness will be small change in x. And this will be the position of center of gravity for this one lamina, for this one strip. But remember, there are many strips. So let rho be the weight per unit area, okay? Then the x-coordinate or the centroid of the lamina above is denoted by x bar. And can be got by taking moments about the y-axis. So let's see how to take moments. Moment of the whole lamina is equal to sum of moments of all the strips. So moment of the whole of this lamina will be equal to the sum of moments of the small strips which divide that whole area or lamina. I think you remember this formula. We already used it under center of gravity of particles, where this is the total weight and this is the x-coordinate of the center of gravity of the whole lamina. Then these ones is the small weight for one strip and the x-coordinate of that strip, and then you sum up all of them. So the total weight will be from x equal to a to x equal to b of the small weight or the small strip. So where this is coming from, remember it is like this, that strip, and we said it has y here and small change in x here. So this is like a rectangle, and when I get area of the rectangle, you multiply the two. So y times small change in x is what gives this. That is area. But remember, we said a lamina has a uniform weight per unit area. So if rho is the weight per unit area and I have the total area, I can multiply the two to get the total weight, which is that. Okay, for this other side, you only deal with each strip. So it's a weight for one strip times the its corresponding x coordinate. And you sum up all of them from x equal to a up to x equal to b. Then to remove the summation sign, I think you see this limit, you bring it, it becomes an integral. So in the limit as x small change in x tends to 0, this summation from here to here will tend to integral. Then we shall remove the constants. This x bar is a constant, that's why it is out. This is a constant, it is out, so I remain with this y. Now this motion in x becomes dx. Then this one is the lower limit, this becomes the upper limit. That is for the left hand side. What about right hand side? So the same, this becomes integral from a up to b. Now this is a constant, but the rest are not. So y and x are not constants, they remain here. Small change in x becomes dx. So when I make x bar the subject, I'll come up with this as the formula used to get the x bar for the centroid of a lamina. So sometimes the length of the strip is too wide, therefore sketching is necessary. That was getting x coordinate. What about getting y coordinate? So you do the same, but this time you take moments about the x-axis. So total weight times y bar is equal to small change in y times a half y. Now why do we say a half y? Let's just go back. It is because for this, I think you'll find out that for as long as there's a line of symmetry, we already talked about it, the center of gravity is at the line of symmetry. And for a rectangle, it is at the midpoint. This intersection is at the midpoint. So this small strip approximates to a rectangle, whereby the whole of this is y. Now this position of the center of gravity must be at the point which is half the total height, which is half y. So that is why we use half y. Then we bring in the limits. Then the integral. So here for this side, this is constant, this is constant. This is there, and this becomes dx. This is constant, this half is constant, this and this becomes y squared, this becomes dx. Therefore, y bar can be given by that. So in summary, that is how you can get the centroid of a lamina. You should realize that the denominator is the area of that lamina. The reason why we put here area of a lamina is because sometimes the shape can be known, can be definite in a way that it has a standard formula to calculate its area. So in such a case, we don't need to again integrate, just code that formula for getting area of that shape and you substitute there. Okay, so now let's go through these questions. Question 1, find the coordinates of the centroid of the area lying in the first quadrant and enclosed by the curve, this x-axis, and the lines this and that. Then part B, enclosed by the curve and the lines. So what is the difference between the two? Between the two, here, it is both are enclosed by this, okay, this. But in part A, they include in x-axis, and here they don't include it there. We are going to see how they differ. Let's begin with part A. Part A, we shall come and draw the axes. Then we shall draw our curve. This y curve means it is symmetrical about the x-axis. I think in your O-level you are used to curves like this, whereby it was x squared. So when they change it, it means that it is now, here it was symmetric about the y-axis, but when it is y which is squared, it means it is symmetric about the x-axis, as you can see it here. Then they said x-axis and these two lines. So that the lines x equal to 1 and x equal to 4. So the area we're interested in is that. It goes up to here. So in this case, this strip, height of the strip is y, and thickness is small change in x. So taking moments about the y-axis means I'm going to get x bar. And getting x bar, I'll simply just code the formula, if I remember it. If not, I go back from first principles as we saw it. So the good thing, I know y in terms of x. Do you see this? dx, meaning that I can integrate when there's still y. So my work is to come here and substitute for y, then I can easily integrate. I'm going to deal with each bit by bit, numerator alone and denominator alone. Then after that, we shall divide the two to get the answer they want. So let's begin with the numerator. Numerator, you have integral of xy dx. So substitute for y, then use laws of indices to get this, and then you can integrate, then substitute in the limits to get the output using the calculator. That was numerator. What about denominator? Still do the same, substitute for y, then integrate, substitute limits, and get the output. Then you can code the formula for x bar, substitute, and get the answer they want. That was x bar. What about y bar? Y bar, still I'll code the formula, then deal with each bit by bit, numerator alone and denominator alone. So y bar was given by this. I already got this, and this one was already got from the previous part when you're getting x bar. So in the end, I'll come up with 3/28. And those will be the coordinates. That was part A. Part B, like I said, they are somewhat similar, but in part A, they mentioned about x-axis. And here, in part B, they did not mention about x-axis, so you should be keen. Now, what is the difference between the two? The difference is that when they don't mention about the x-axis, we look for the entire area enclosed by this curve and the two lines given, which is that. And you realize that now the height is 2y because we have this y and also this y to give you 2y. Thickness is small change in x. So, and here, this one is symmetrical about the x-axis, meaning that the center of gravity lies along y equal to 0. So taking moments about the y-axis, you code the formula. Then realize that now we're using 2y, not y, because this, that. Then we shall deal with each numerator alone. Use this one substitute for x, integrate, substitute limits, get output. Then also this one, substitute for y, simplify, integrate, substitute limits, and output. Then code the formula for x bar, substitute, and get the output. And those will be the coordinates. That was question 1. Now we shall go to question 2. Question 2 says, prove that the center of gravity of a uniform semicircular lamina of radius r lies on the axis of symmetry at a distance 4r over 3 pi from the straight edge. So there we need to make a sketch. Shall draw the axes and label them. Then they want semicircular lamina of radius r. So I put a small strip inside. The height is still 2y, and the thickness is small change in x. From here to here it is x. And from here to here it is radius. Meaning that I can use Pythagoras theory. From Pythagoras theory, I'll come up with y being equal to square root of r squared minus 2 minus x squared. So taking moments about the y-axis, meaning I want to get x bar. I'll code the formula. Now, the good thing, this shape is standard and is known to have a specific formula for getting its area. That's why I've used area over semicircle. Then come and get the numerator. So this substitute for x, substitute for y, integrate, simplify, substitute limits, and get the output. That was the numerator. The denominator, we already know that it's area of a semicircle. And area of a semicircle is a half pi r squared. So in the end, we'll come up with this, which is required. Question 3. Prove that the center of mass of a uniform sector of a circle, center O, radius, I think radius should have been r, radius r, which subtends an angle to alpha is at a distance this from O. So you come and make a sketch. So I need to make a sketch of a sector. Sector is a part of a circle, but the side subtends an angle to alpha, meaning we have split it into 2 alpha alpha to get the 2 alpha, and the radius is r. So from the diagram, the center of gravity G of the wire lies on the x-axis here, which is because it's the line of symmetry, which is true. So let it be at that point G. Now, if we divide the lamina in 2 sectors, then each sector is approximately a triangle with a center of gravity G prime at a distance 2/3r from O. Now here, some of you are wondering where this is coming from, but it's a standard formula if you look at your logbook. Center of gravity of a triangle, but the good thing, we are also going to look at it in this video. So if it confuses you where it comes from, first leave it as it is and work and copy the solution as it is. Then after going through the center of gravity of a triangle with you, you'll be able to identify how it comes about. So let's first redraw to avoid congestion, redraw the sector and show the element. So if we take that small strip, it approximates into a triangle with center of gravity G prime. So now shall let rho be the weight per unit area. Then we shall come and tabulate. Have the body, weight, x, coordinate, and the product. So for the element, remember we said it approximates a triangle, so to area would be a half r squared small change in theta times the rho to give you the weight. Why is it that? Because of small angles. I think remember that for small angles, okay, let's just sketch it here. This is theta, r. So area will be I have AB sine theta. So A and B are R, so I have times R to give you R squared, then times sine small change theta. But remember that sine of a small angle approximates to that very angle. So that's why here we don't see sine there. We just see the angle because that's a small angle. Then x coordinate, we already saw it on this diagram. Then multiply the 2. Then for a sector, the area is that I have R squared times 2 alpha. Now, why is it so? Remember, area of a full circle would be pi r squared. Then what about area of a sector? It will be the angle times, it will have been 360, because the angle is in radians, we use 2 pi, because we know, I believe by now we know that 360 degrees is the same as 2 pi radians. So realize that this pi and this pi cancels. Then this one comes here to become a half times 2 alpha, which is here. So that's how it came about. Then the x bar, we don't know it. Multiply the 2, you'll come up with that. So next is to take moments about the y-axis, meaning I have to get x bar. So that is the formula. Sum of moments is equal to moment of sum. Then you substitute. The whole of this is here. And this is here. But there's x bar here. So this summation sign becomes integral. I think by now you know why. And this small change in theta becomes d theta. Then we integrate from negative alpha to positive alpha, because in the end you have to get 2 alpha. So here I realize that this and this will cancel. Then this r squared removes 2r to remain with only 1r here. So the good thing, r is a constant, meaning I can integrate this to get this. Substitute limits. Simplify. Sine of a negative angle is equal to negative sine that positive angle. That's why here it was minus, but because of this negative sign, it becomes positive here. Collect like this and this, collect like times to give you this. Then make x by the subject, and that's what they wanted. That was question 3. Now question 4 says, prove that the center of gravity of a uniform wire bent into the form of an arc of a circle of radius r and subtending an angle 2 alpha at the center is at a distance this from the center. So you come and draw the axis, make a sketch of a wire. So that is the wire bent in form of an arc and subtending an angle 2 alpha at the center, at the origin. This is the radius. So from the diagram, the center of gravity of the wire lies along the x-axis, which is the line of symmetry. Okay. What about a small element of that wire chosen? So if we divide the wire in 2 small arcs subtending an angle small change in theta at center, then each element of length this is approximately a particle. So from here up to here, the length is r sine small change in theta. Now this one, I've just resolved this radius to give you this. Then this one is r small change in theta. So let rho be the weight per unit length of the wire. Then you come and tabulate something. So the element, we have that, length times weight, then x coordinate and the product. Then for the whole arc, we have that, then that, and then apply the two. So I shall repeat the same procedure. Take moments about the y-axis, you come up with that. Summation sign becomes integral sign. Simplify and integrate. Substitute limits. Simplify, collect like terms, and get x bar. And that's what they wanted. Then question 5, show that the center of gravity of a uniform thin hemispherical cup of radius r is at a distance r over 2 from the base. They said uniform thin hemispherical cup, meaning it is hollow. So shall come and first make a sketch. Hemispherical cup, center of gravity will be at that point, and then that will be the element. So let's first redraw the element on another axis to avoid congestion. That is radius. So when I resolve this, vertical I'll come up with this, and horizontal I'll come up with this. So from the diagram, the center of gravity lies along the x-axis, and we showed it here. If we divide the hemisphere in two slices parallel to its plane face, each slice is approximately a circular ring with its center of gravity at its center. These are the circular rings they're talking about. So for considering the ring, it is approximately a cylinder of radius this and width that. Therefore, the surface area of the ring will be this times this. Now, where is it coming from? Remember, they told us the ring approximates to a cylinder of radius r sine theta, and height is r small change in theta. So if I get the surface area will be circumference, which is 2 pi r, 2 pi times this radius, then times the height, which is r small change in theta. Correct like terms, you come up with this. Let rho be the weight per unit area. So shall tabulate, shall get the element, which is that, the area times rho, then the x coordinate is that, product, then for the hemispherical shell, weight is that, area is this, surface area, because surface area of a sphere is 4 pi r squared, meaning surface area of a hemisphere will be a half times 4 pi r squared, which is 2 pi r squared. X coordinate, I don't know it, then multiply the 2. Then take moments about the y-axis, so this should be y. Because if you want to get x bar, you have to take moments about y-axis. So you substitute, then summation becomes integral, simplify, then you integrate, substitute limits, simplify, and get the x bar, and that's what they wanted. So now we shall go to standard centers of gravity of uniform lamina. The center of gravity of a uniform lamina lies on the line of symmetry that the lamina possesses. I think you already know that. So yeah, the main aim in these shapes is to identify the lines of symmetry. So let's start with a uniform rectangular lamina. When you have a rectangle, you just get this line of symmetry, and that will be the center of gravity. For a circle, its center is the center of gravity. Then for a semicircular lamina, good enough, we have proved it, that center of gravity of a semicircular lamina is this from the base, from the flat surface. Like that. So from here to here, it is 4r over 3 pi. Then for an equilateral triangle, this is what I've been telling you. So by geometry, an equilateral triangle has 3 lines of symmetry. There's that, there is that, and there is that. They all meet at a point G, which will be the center of gravity. Now, if you can try to draw it accurately, you'll confirm that the distance from the base to here is a third of the whole of this length. And that is why that's what we base on to come up with the position of the center of gravity for a triangle. So previously we said 2 over 3r. You remember when we say that this approximates to a triangle with r, and they say this center of gravity is 2 over 3r. Why? Because if from here to here is 1 over 3, then the balance should be 2 over 3 from the vertex. Therefore, if we are measuring center of gravity from a vertex of a triangle, it will be 2 over 3 of that length, median. Then if you are measuring it from the base, then it will be 1 over 3 of the length of the median. As simple as that. So if AD is h, then DG is 1 over 3h, and AG is 2 over 3h. But that does not work for only equilateral triangle. It works for all triangles. It works for all triangles. So let's start with an isosceles triangle. So there, the center of gravity still will be at that point, such that if AD is h, then DG will be a third, and AG will also be 2 over 3h. It also works for a right-angled triangle. Now, what is D? You have been seeing us getting D. This D is called a midpoint, only that for an equilateral triangle, the midpoint here, from the vertex to the midpoint, it makes an angle of 90 for an equilateral triangle. For an isosceles, if this is from the vertex enclosing the two equal sides, then it still makes an angle of 90 here. But if you draw another line from here to here, it will not make 90, it will make a different angle. So that is why here you are not seeing the 90 degrees here, because it can't do that. That property is only for isosceles and equilateral. So here what we do, we just look for the midpoint of BC and join from the vertex to that midpoint. Vertex to that midpoint. The intersection will be the center of gravity. So in this case, that is an intersection. If you know, in most cases they will not give you this length, but if they give it to you, then it still follows the same property, that AG is 2/3 of AD, and also DG is 1/3 of AD. But usually in most cases they give you this length and this length. So what do? What we do, we just drop a perpendicular from the center of gravity, and we say that now EG is equal to a third BA. And also drop a perpendicular here and say FG is equal to a third BC. We're using the word a third because it is coming from the base. So that's what I've been talking about. Then uniform triangular lamina. So this does not in general have any line of symmetry. I think we saw for that for a right angle triangle there was no line of symmetry, but it still followed the rules that from the vertex it meets the midpoint of the other opposite side. So that's what we also use. Therefore, the position of the center of gravity of a uniform triangular lamina without lines of symmetry is the point of intersection of the medians. And that's how they draw medians. This is the centroid of the triangle, and it is 2/3 of the way along each median from the vertex, where D is the midpoint of BC. So I think let's first draw it for you to know where D, E, and F are. So that will be the midpoint of BC, and this from here to here is called the median. Intersection is the center of gravity, but like I told you, they rarely give you this. So what you do, you drop a perpendicular to get the height. So you have to get the height AF and use it to get this GE. They will have located the position of the center of gravity, the y coordinate of the center of gravity. Then also, so now that we have seen individual centers of gravity of individual laminas, we shall look at now composite laminas. Composite means two or more parts of individual laminas are combined to form a composite lamina. So they will still use the same principle that the sum of moments of all individual parts will be equal to the moment of the whole lamina when all parts are added, just as we did for center of gravity of particles. So let's see how to go through these questions. Question 1 came from UNEB 2015 paper 2 question 15 and says, the figure below shows a lamina formed by welding together a rectangular metal sheet and a semicircular metal sheet. Find the position of the center of gravity of the lamina from the side OA. Side OA is here. So they want the x coordinate. So you shall remember that for a lamina, it has uniform weight. So let rho be the weight per unit area. So we shall tabulate. So always shall be tabulating, provided it's composite lamina or composite solids. For Centroids, that's when we integrate. So you come and put a column of figure, a column of weight, and a column of the x-coordinate. Why? Because they said distance for the center of gravity from side OA. OA is now the y-axis, so you're doing moments about the y-axis, meaning you'll be getting x values only. So we shall go step by step. Let's start with a rectangle. Here there are two shapes. There is this rectangle and there is this semicircle. So for a rectangle, weight is area times rho. So area is length times width, which is 4 times 20 to give you times rho to give you 80 rho. Then the x center of gravity for a rectangle, it is the line of symmetry, meaning that the x coordinate will be half of this. Okay, then another shape will be a semicircle. Semicircle area is a half pi r squared times rho to give you 12.5 pi rho. Then the center, it is along this, so that is from here to here, it is 3 pi, is it 3r or 4r over 3 pi? 4r over 3 pi, okay? Now, remember they want us to measure from here, meaning that to reach here, I'm going to first measure from here to here, which is 4. That is why you see 4 here. Then I add on from here to here, which is 4r over 3 pi. You see this? 4 times r, which is 5, radius is 5 based on this, over 3 pi. Then I simplify to come up with this. So that will be the value of x. Then for the whole lamina, total weight is got by adding these two. And the final position vector is unknown, so we call it x bar. So that is the table we shall be using to take moments. We shall just multiply this with this, this with this, and this with this. So taking moments about OA, we shall come up with this plus that equal to that. So these are the individual parts which make up a whole lamina, and this is the whole lamina. Then you simplify and get x bar, and that's what they wanted. Question 2 came from UNEB 2008 paper 2 question 8 and says, find the coordinates of the center of mass of the lamina shown and take A as the origin and AB as the x and y axis. So this is our origin, x axis, y axis. Okay. So we shall come and first put the axis they told us, x axis, y axis. Then we let rho be the mass because they said center of mass. So this will be mass per unit area. Now these ones, this is the trapezium, but we have not yet looked at, we have not seen a standard center of gravity of a trapezium. So what we need to do is to split it into two, so that we get this square and also this right angle triangle and this right angle triangle. Then we can now tabulate. So we have a figure, we have mass, we have x coordinate and the y coordinate. We shall get both because they just said coordinates, unlike in question 1 where they specified. So we shall go shape by shape. Let's start with ABFE, which is the square. The area will be length times width, which is 3 times 3 times rho to give you 9 rho, which is the mass. Then the x coordinate, remember it is half half. So Half of 3 is 1.5. Half of 3 is 1.5. That's how you can get x coordinate, y coordinate. The next will be now triangle BCF, this one. So area is a half base height times rho to give you 4.5. Then the center, remember you drop a median. So therefore from here to here, okay, remember I'm measuring from this. We begin with x value. So for x value I'm measuring from here, so I'm going to measure from here up to here. How can I get that distance? To get that distance, I think you remember what we did about right angle triangle. This is what we did. If it was like this, and the center of gravity, it means that if I measure from here up to here, it will be a third of the whole of this. Then also if I measure from here up to here, it will be 2/3 of the whole of this. Therefore, from here to here, it will be 2/3 of the whole of BF. 2/3 times 3 to give you 2. We're using 2/3 because we are starting from a vertex. Okay. Then for the y-axis, for the y, we are starting from the base. You see this? It is a base and you go up. So it is 1/3 of the whole of this height. But remember, we have to start from this axis. So there is already a 3. Therefore, we're going to first say 3 plus a third of CF, which is 3. How do you know that CF is 3? It is because from here to here it is 3 and from here to here is 6, meaning the balance must be 6 minus 3. Then next will be triangle CDE. CDE still, area is a half base height times rho to get weight, which is 24 rho. Then here, I want to first get the x coordinate. So from here to here, I already know it is 3. What about from here up to here? It is from the base, so it will be 1/3 of the total, which is 8, to give you 17/3. Vertically, it is still from the base, so it will be 1/3 of this total, which is 6. So 1/3 times 6 to give you 2. Then for the whole lamina ABCD, area was got by adding all these ones, total weight, to give you that. Then here you don't know it, so you call it x bar. You don't know it, so you call it y bar. And that will be the table to help us take moments. Taking moments means we just get, actually this gives you the position vector of where this mass is centered. So this will go with this, this will go with this, this will go with this, equal to this with this in vector form. So simplify, take this one this side, and that's what they wanted. Then question 3 came from UNEB 2012, paper 2, question 13b, and it says, the figure below is made up of a hemispherical cup of radius 7 centimeters and then to a circular base of the same material and the radius 7 centimeters. The mass of the stem is 1/4 that of the cup. Okay. Find the distance from the base of the center of gravity of the figure. So let rho be the weight per unit area of the figure. Then you come and draw a column of figure, weight, and y coordinate. So for a hemispherical cup, weight will be surface area times rho to give you 98 pi rho. Then the center of gravity, remember we are measuring from the base. So from here to here is 7, then you add on from here to here, which is a half r. Therefore it will be 7 plus a half times 7, which is 10.5. Then for the stem, here they already told us that the mass of the stem is a quarter that of the cup, which is this. So mass of the stem is a quarter, meaning that the weight is also a quarter that, which is gives you 24.5 pi rho. Then the center is here, which is just half of 7. Then for the circular base, weight is area times rho to give you 49 pi rho. But the center of gravity is here, meaning it is 0, because that's the reference point. Then for the whole lamina, weight, you add all these ones, come up with this. Then here you just put y bar. Then you can take moments. This with this, this with this, this with this is equal to this with this. So that is moments, then you simplify and get y bar. And that's what they wanted. Question 4 came from UNEB 2023, paper 2, question 8. That was last year, actually this year. It says a uniform lamina in form of a square with side 60 centimeters has a circular hole of radius 20 centimeters made in it as shown in the diagram below. Find the position of the center of gravity of the lamina from side AD. So from side AD, they want the x-coordinate. So let rho be the weight per unit area of the lamina. Then you shall make a column of the figure, weight, and the x-coordinate. For the square, for the whole square, the weight is, area is this times that times rho to get the weight. Then the x-coordinate is half of this, which is 30. For the circle, area is pi r squared times rho to get the weight. So for the circle, remember we are measuring from here, so we have to get the distance from here up to here. So you can either just say 60 minus 20 to give you 40. It is still okay. Then for the remaining lamina, remember initially it was the whole of this square, then they removed off this circle. So the balance will be got by subtracting. So this minus this, what do you get? That will be the remaining weight of the remaining lamina. And this center of gravity is what we want, so we shall call it x bar. Then we can now take moments, which gives you that. Then you simplify and make x bar the subject. And that's what they wanted. Then question 5 came from UNEB 1999, paper 2, question 16, and it says ABCD is a uniform rectangular sheet of cardboard of length 8 centimeters and width 6 centimeters. A square and a circular hole are cut off from the cardboard as shown above, which is here. Calculate the position of the center of gravity of the remaining sheet. So shall let rho be the weight per unit area, and then we tabulate. So we need a column of the figure, weight, x-coordinate, and y coordinate. So let's begin with a whole lamina, ABCD. It's a rectangle, meaning that what will be area times row to give you 48 row. Then this is half of this 8. Then y coordinate is half of this 6. Then for the square, this square area is 2 times 2 times row to get the weight, which is 4 row. Then the x coordinate from here up to here. So from there to there, this is 2 and this is 1. Now, how did we find out that this is 2? Let's check. 1, if this, let's start with this. This is also 1. Is it true? Okay. And from here to here, it is 2. Now, let us first add everything and we see 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 2 is 6. Now, but remember here there is 8. So if from here to here is 6 and from here to here is 8, it implies that this small part here is 2. Okay, therefore this center of gravity here, it will be now 2 plus 1, which is 3. Then y value from, now the question is, what about from here up to here? What is it? You can see here, this is the whole of this is 6, but here we have 1 plus 2, which is 3. Here the balance will be 3. So from here to here it is 3. Therefore it will be 3 plus 1, which is 4. Alternatively, you can just choose to do like the way I did here, which is 6 minus this from here to here, which is 2. It also works. That was the square. What about the circle? Circle area times row to get the weight. Then the x, the good thing we know that from here to here is 8 and from here to here is 2. So the x coordinate will be 8 minus 2. Then also sum applies this from here to here is 1, from here to here is also 1, and the whole of this is 6. So it will be 6 minus 2. Then the remaining lamina, after removing those two, will be got by saying this minus, open brackets, this and that, which gives you that. We don't know this, call it x bar, and this call it y bar. Then we can take moments. So these values are got from the table. Then you simplify, take this one this side, and use a calculator. That will be the position of the center of gravity. So that has been center of gravity of composite lamina, but now we need to add in something about something in these composite laminas, and that is called suspending a lamina. So whenever a lamina is suspended from a certain point, equilibrium is only possible if the lamina hangs so that the line of action of its weight passes through the point of suspension of the lamina and its weight, as shown below. So let's consider a simple lamina, which is a rectangle. It has weight like that. Now, what if I suspend it from a point, say A? That's how it will appear. And because this is in equilibrium, the weight must pass through 2 points. One, the point of suspension, and yet must also the point of suspension and the center of gravity. Do you see this? This is a straight line, meaning that it is in equilibrium. Now redrawing this, because this is a simple lamina, but in the questions there will be more than it will be a composite lamina. So it may be difficult for you to redraw it when you have suspended it. Now, what do you do in such a case? You have to just remember that when it is suspended, the line of action passes through the point of suspension and the center of gravity. Therefore, after calculating the center of gravity, you just draw two sides. For example, here they said you suspend it from this point. So you come and draw just two sides, this and this, which is here. Then from there, you have already calculated your center of gravity, so you locate it. And after locating it, you just draw a line, a straight line from this point of suspension through the center of gravity. As simple as that. Now, the angle they will tell you, for example, they may want the angle AB mixed with the vertical. It will be this. Or they may also want the angle AD mixed with the vertical. It will be beta. Like that. So you don't need to use a lot of ash to redraw it when you have suspended it. Just remember that the line of action passes through the point of suspension and the center of gravity. As simple as that. If they ask for the angle it makes with the horizontal, it means you say 90 minus theta and also 90 minus beta respectively. So with that, we shall go through this question. It came from March UNEB of March 1998, paper 2, question 16, and says the figure ABCDEFGHIJ shows a symmetrical composite lamina made up of a semicircle of radius that, rectangle that, and another rectangle with the dimensions. Part A. Find the distance of the center of gravity on this lamina from IH. So they want Y values. I think let's start with part A. So let rho be the weight per unit area of the lamina. Then we tabulate. We need the column of the figure, the weight, and the coordinate. So we start with GHIJ. We shall start with this lower one. Weight is area times rho. Then the y coordinate, half of 4. Then we shall go to CDEF, which is this. Weight is area times rho. And center of gravity, we already have this 4, then plus half of 8, which gives you 8. Then we have semicircle, area times rho to give you the weight. Then the center of gravity, we have from here up to here, which is 4 plus 8. Then from here to here, it is 4r over 3 pi. So 4 plus 8 plus 4r over 3 pi to give you this. Then for the whole lamina, you add all this weight. And then here you put an unknown. Then you can take moments. And simplify to get the value of y bar. And that's what they wanted in part A. Then in part B, they said if the lamina is suspended from H by means of a peg through a hole, calculate the angle of inclination of HG to the vertical. So we shall come and draw the two sides IGH. Then we draw a line. We first look at the position of the center of gravity, which I've got. I think this is there. Now, where did this 3 come from? It is because HI was actually the whole lamina was symmetrical, and the whole of this was 6, meaning this is 3 and this is 3. That's why you say here 3. So you can draw your straight line. The said angle GH makes with the vertical, which is this. So I can get it using tan this over this. And that will be 24.07. And that's what they wanted. Then question 2, a uniform lamina ABCD is in the shape of a trapezium, in which AB is that, AD is that, this is that, and angle DAB is 90. Part A, find the distance of the center of gravity of the lamina from AB and AD. So you need to first make a sketch of that trapezium. And divide it into two shapes, rectangle and triangle. Then let rho be the weight per unit area. Then you can now tabulate. You need a column of figure, weight, x and y coordinates. Let's start with the figure of AECD. This one, which is a rectangle. Weight is area times rho, which is that. X coordinate will be half of 2a. Y coordinate half of 6a. Then the triangle area is that times this to get weight. So x coordinate, remember we measure from here up to, so let's just look at, we're going to measure from here up to here. So from here to here is already 2a. Then from here to here is a third of 6a. So this should be a third. Here it should be 3 to get 6a over 3 to get, you get 2a plus 2a to get 4a. Then here also from the base, it is a third of this 6a. Then for the whole lamina, total weight to add all this, and here we put an unknown, Then you can take moments. So that the moments you simplify and then make x bar y bar the subject. And that's what they wanted. That was part A. What about part B? Part B says the lamina is suspended from A and hangs freely. Find the angle between AB and the vertical. So we shall come and draw the two sides enclosing A. There is AB and there is also AD. Center of gravity is that. Therefore, we can now get the angle they want, AB, using tan. And that's what they wanted. Then question 3, ABCD is a uniform rectangular lamina in which AB is 32 centimeters, AD is 20 centimeters, P and T are points on DC and AB. Actually, they're here, this and this. Okay. Such that PC is 9 and TC is 6. 9, 6. A triangular portion PCT and a semicircular portions with diameters OX, OY, and XY, all these ones, are removed from the lamina as shown. Find Roman 1 the distances of the center of gravity of the remaining lamina from AD and AB. So let's start with that. So one, we shall let rho be the weight per unit area. Then we shall tabulate and put columns of figure, weight, x and y coordinates. So let's start. The whole lamina area will be 32 times 20. Then multiply by rho to get the weight. Then x, half of this is x and half of this is y. So half of 32 will be x and half of 20 will be y. Okay. Then for semicircle OX, radius is 3. Therefore, area will be that multiplied by rho to get the weight. Then x coordinate, that is G1. So from here, T is 20, and from here, T is 9, meaning the balance is 11. Okay. Also, from here, T is 32. And from here, what about from here, T? Because we know that from here, T is 12 plus 12, which is 24. Again, the balance should be 32 minus 24, which is 8. Okay, now if I want to get this position, I'll get this, which is 8 plus 3 to give me 11. Okay, then for the y coordinate, I know that from here T it is 11, and from here T is 4r over 3 pi. So it should be 11 minus 4r over 3 pi. Let's fill those ones in. First one, it is 8 plus 3. Next one is 11 minus 4r over 3 pi, which gives that. The another one will be semicircle OY. OY, center of gravity is here. So from here, T is 8 plus 6 plus 3. 8 plus 6 is 14. 14 plus 3 is 17. But the y coordinate is the same as G1. So here you're going to put, first of all, area is still also the same. X coordinate is 17, and this one is same as the one for OX. Then next will be semicircle XY. For semicircle XY, from here to here, it is 8 plus 6. And from here to here, it is 11 plus 4r over 3 pi. So let's say substitute area times row to get weight. 8 plus 6 to get 14. 11 plus 4r over 3 pi to get that. Then for PCT, that triangle, so from here up to, from here to here, it is 2/3 of 9. What about from here up to, okay, the easiest is this. From here to here, is 1/3 of 9, but the whole of this is 32. So it will be 32 minus 1/3 of 9, minus 9 over 3. Then the same applies to y, it will be 20 minus 1/3 of 6. That is the weight. Then 32 minus 1/3 of 9, 20 minus 1/3 of 6. Okay, then for the remaining lamina, we subtract this minus the whole of this. You'll come up with this. Here you put an unknown. So that table we can now take moments. Then we simplify. Collect like terms. So what I've done, I've taken all these ones this side. Then bring this one this side and use a calculator. And that's what they wanted. So that was Roman 1. Roman 2 says, find the angle AB makes with the horizontal when the remaining lamina is hung from B, from here. So here we shall need to first redraw the two sides enclosing the point B. Then we locate the position of the center of gravity. So this is here. Now this one, remember the origin was here. So from here to here is this one. So the remaining part will be that. The angle AB makes with the vertical is theta. Therefore I can get it from that. And that's what they wanted. So now we shall go to centroid of a solid of revolution. So these are the same things that are covered in Math 1, but they are also examinable in Math Part 2. That's why we shall repeat them. So in Math 1, what is common is calculating the volume of a solid of revolution. But here we are interested in the centroid of a solid of revolution. So let's consider a curve y equal to fx read through 360 degrees above the x-axis as shown above, and the ordinates is x equal to a, which is here. Then the curve y equal to fx, which is there. Then you rotate it through 360 degrees above the x-axis to get this. So that is the whole figure story they want. But we are going to slice it into, we're going to cut it in two slices. Those ones. So those are similar, approximate to circular disks with radius y and thickness small change in x. So that is the radius and the thickness. So thickness is small change in x. So now we are going to see how to take moments, but before that we have to let rho be equal to the weight per unit volume. And x bar be the coordinate of the center of gravity of the whole solid. And it's good by taking moments about the y-axis. So we are taking moments about y-axis to get x bar. So the moment of the whole solid is equal to sum of moments of all the disks. Moment of the whole solid is weight, total weight times x bar. And here, weight of each slice and its position, x coordinate. Then you sum it up. So this weight is volume times rho. This is volume of a small disk times rho. Then you sum all of them times x bar. Then here still volume times rho times the x coordinate. Then you put integrals. The summations become integrals. This and this cancels. Then you remain with that. Make x bar the subject. And there is it. So in summary, you can either use this. Now where is this coming from? That is coming from here. Where only rho cancels and remain with this pi, which gives you this, and this one which gives you volume times x bar. So this works like we did for laminas. It works when the shape of a lamina has a standard formula for calculating its area. Even here, when the shape of a solid has a standard formula for calculating its volume, then that's when you can use this. If not, then you have to use this like that. So those are the two ways of getting x bar. And with that, we shall go through these questions. Question 1 came from 1996, part 2, question 9b, and says, the area enclosed by the curve this and the lines these ones lying in the first quadrant is rotated about the x-axis through one revolution. Find the coordinates of the center of gravity of the uniform solid so formed. So I need to make a sketch of the curve and the ordinates x equal to 2 and x equal to 4, and that would be the area. When you rotate, it goes also downwards, and this is small change in x. So taking moments about the y-axis, it means we are going to get x bar. So we know that x bar is given by this formula. Let's deal bit by bit. Numerator alone, we come up with that. Denominator alone, we come up with that. Then we can divide. When we divide, we shall be able to get x bar. And that's what they wanted. Then question 2 came from UNEB of 2001, paper 2, question 16a, and it says, prove that the center of mass of a solid cone is a quarter of the vertical height from the base. So we shall come here and make our sketch. Of a cone. So we have chosen to put the base of the cone on the y-axis. It is okay if you put it on the x-axis. It is also still okay. So here for me, I'll be looking for x bar. If you put on the x-axis, it means you'll be looking for y bar. But for consistency, since even in the derivation of the formula to use, we used x bar, we derived x bar, then let's maintain the x bar. That is a small element, a small disk. Then here this is O0R, and here it is H0. Those the coordinates are to help us get the equation of this straight line, which was rotated. So equation got by equating gradients, which is this. So taking moments about the y-axis, we have that formula. So the numerator, good enough, we have y, so numerator we shall substitute for y, simplify, and then integrate. So let's do that in the next slide. Then we substitute limits. Here substitute limits and open brackets and simplify. Then you remember that x bar is equal to this numerator which you've got, divided by volume of a cone, which is a third pi r squared h. It gives you that, and in the end you come up with a quarter h, because the whole of this will go and remain with one h, then here and this will remain with a quarter, and that's what they wanted. Then question 3, prove that the center of gravity of a uniform solid hemisphere of radius r lies on the axis of symmetry at a distance 3r/8 from the plane surface. So still we do the same, we get to make a sketch. So the flat surface lies on the y-axis. Then we draw a slice which will be rotated. So you are going to use this right angle triangle to get the relationship between y and x. So by Pythagoras theory, we have got the relationship between y and x. Therefore, taking moments about the y-axis, we have that. Therefore, come and substitute for y squared. Simplify, then integrate, substitute limits, output. Then I can substitute back into the x bar. This divided by volume of a hemisphere, which is that. It gives you that, then you simplify to get that which they wanted. So it's a summary of the standard centers of gravity which are also available in your mathematical logbook and can be used when necessary. So now we shall go to center of gravity of composite solids. Question 1 came from UNEB 2001 paper 2 question 16b, and it says the figure ABCDE below shows a solid cone of radius r, height h, joined to a solid cylinder of the same material with the same radius and height h. If the center of mass of the whole solid lies in the plane of the base of the cone where the two solids are joined, find h. Here. Now this is another part, we shall deal with it, but let's just deal with this part of finding h. So shall say let rho be the weight per unit volume. Then shall need columns of the figure. weight, and the y coordinate. Why? Because it is symmetrical about that. So for the cylinder, volume times rho to get weight, then here it will be half of h for the cone, volume times rho to get weight, then here it will be, from here t is h plus a quarter h to give you this. Then for the whole lamina or whole solid, now add this with this to give you this. Here you don't know, put an unknown. So taking moments, you'll come up with that. Simplify, come up with that. Let's call it equation 1. Then shall remember what they told us, that if the center of mass of the whole solid lies in the plane of the base of the cone where the two solids are joined, then y bar is equal to capital H. Let's go back to the diagram and see. The center of gravity lies, the base is here of the cone and the cylinder, so, and the vertical height from here, it will be capital H. So shall come and substitute for y bar. Then we simplify and see how to make capital H the subject. So collect like terms, put square root on both sides, make capital H the subject, and that's what they wanted. So that was the first part, but there is also another part. This part says that if instead capital H is equal to small h and r is equal to a half h, find the angle AB makes with the horizontal if the body is hung from A. So that means that from our equation 1 here, where there is capital H, we are going to replace it with small h. So let's do that. So that was equation 1, then substitute small h with capital H with small h. Then we simplify, collect like terms, then make y by the subject. So now I can, they want the angle, so I'm going to redraw. It was being suspended from A. Put the center of gravity, that is a half h. Then that will be the balance, you need for h minus that to give you 5/16h. Then that will be the weight. Then the angle AB makes with the vertical is that, which will be 57.99. Then the angle it makes with the horizontal to be 90 minus that to give you 32.01. So that was question 1. Now we shall go to question 2. It says, the figure below shows a uniform hemispherical solid of radius 30 centimeters with a cylindrical hole of radius 5 centimeters and height 10 centimeters centrally drilled in it, as shown. Find the distance of the center of gravity of the figure from the flat surface. So we are going to redraw it so that the flat surface faces downwards. Okay, So now we can let rho to be the weight per unit volume, and then we tabulate. So we shall need a column of figure, weight, and the y coordinate. So starting with the solid hemisphere, weight will be volume times rho to give you this. So the center of gravity of the hemisphere will be 3r over 8. So 3 over 8r to give you this. Then we have a cylinder, volume is that, times rho to give you the weight. Then the y value will be half of 10 to give you 5. Then the remaining solid, you subtract this minus this to give you this. And here it's unknown. So now we shall take moments about the x-axis to get y bar. Then we simplify, collect like terms, and get y bar. And that's what they wanted. Then there's also another part where they said if the figure is placed on an inclined plane with the flat surface in contact with the plane, calculate the angle that the plane should be inclined before toppling occurs, assuming that sliding does not occur. So condition for toppling, I think remember it. The good thing we have seen, they got the center of gravity which is there. So for toppling not to occur, this weight must pass through this corner. And this will be the angle they want. So we have this and we have that, so we shall use tan. Therefore it will be tan 30 over 11.2937. And that will be the angle they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on work, energy and power. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we all benefit as a family.